So this is going to be the last lesson in our chapter. It's kind of a culmination of everything. It involves derivatives, it involves implicit differentiation, and we wrap all that together with some fun word problems here. So get excited. Let's have some excitement for related rates. That's what this section is all about. It's about related rates. Okay. Hopefully you had a chance to watch the other YouTube video to kind of get into the idea of what we're going to be doing. But I'm just going to start by reading example 1 pretty slowly and then kind of explaining what our process is. Okay. So this says, a spherical balloon, so we're dealing with a sphere, expands because of solar radiation. Exciting. If its radius r increases at the rate of 2 centimeters per minute, how fast is the volume changing at the instant when the radius is 4 centimeters? Okay. Now, I will start off, not trying to scare you, but I will say this is about as basic of one of these problems as I can give. Again, that's not to scare you because it does sound pretty confusing, but I'm going to try to break this down for you guys, I think pretty easily, in my opinion. But in general, what a related rates problem is, it's when you know the rate at which something is changing, like they'll tell you. Like here they say the radius is increasing at a rate of 2 centimeters per minute. Like they're giving you the rate at which something is changing. And then they're asking you to find the rate at which something else is changing at a certain point in time. Okay? That's when you know you're dealing with a related rates problem. So I'm going to give you guys a little acronym that I think is very, very helpful when you're solving a related rates problem. And I would write this down somewhere, but the acronym is going to be DREADS. DREADS. So anytime you come across a related rates problem, I would immediately think DREADS. Now let me explain what DREADS is and how to go through it. So the first D is a drawing. You're going to be dealing with some geometric figures, and when you are, it could help to sketch a drawing, as you'll see as we go through some of the notes. Sometimes this is helpful, sometimes it's not, but we'll get into that. The next R is rates. We're going to list out the rates. There's always going to be 2 of them because they're always going to tell you one. So we list out the rate we know. They're always going to give you one. And then we're going to list out the rate we're trying to find and at what point are we trying to find it. So rates. The E is then we're going to need an equation. An equation that links our letters together. So I'm going to go through the first problem. I'm not going to talk about the last 2 yet. I'm going to go through the first problem, just kind of doing the first 3 steps of DREADS so you can kind of see what I'm getting at here, okay? So it says we're dealing with a sphere. I would draw a sphere. Does it have to be perfect? No. But just a sphere to get kind of into the problem. Now, this is going to be super, super important. You cannot put any numbers in the picture if they are numbers that can change over time. And what I mean is this. Notice it says we're trying to find how fast the volume is changing at the instant the radius is 4 centimeters. I am not going to put 4 for my radius in this picture because 4 is a number that can change over time. So all I'm going to do is put R as my radius. I'm just going to list an R there. So that's D, that's the drawing. The next R in DREADS is the rates. Now here's how we notate. The notation is going to be super important. We know the rate of change of radius. And the way we notate, for rate of change of radius, we're going to put dr dt. All of our stuff is in terms of time. All of this stuff is changing over time. So dr dt. This means the rate of change of radius. And we know that it's 2. It tells us it's 2 centimeters per minute, so we're going to put 2 for the rate of change. We're looking for the rate of change of volume. And we're looking for it when the radius is 4. So we're looking for dv dt. That's what we're trying to find. And here's some notation. We want this when, we put a little vertical bar here, when the radius is 4. So you'll see this notation a lot of times. So we know the rate of change of radius is 2. We're looking for the rate of change of volume when the radius is 4. So I want to stop right now. We did the D, and then we did R. We did the drawing, we did the rates. The next one is an equation. I need an equation that links our two variables together with our scenario here. So we're dealing with a sphere and volume and radius. So our formula for volume of a sphere is going to be 4/3 pi r cubed. 4/3 pi r cubed. I've been told if you're dealing with three-dimensional figures like volume and surface area, the formulas will be given to you in the problem. They won't be something you have to know. And so since AP does that, I'll do that on my tests as well. You will need to know any two-dimensional shapes. So if you're dealing with area of a circle or circumference of a circle, stuff like that, you're going to need to know the 2D formulas, but not 3D. So now I'm through part 3. The next step is the most important step. But before we do it, I want to tell you the biggest red flag in these problems, the biggest thing students do wrong. Students will plug in numbers too soon. Just like I couldn't plug 4 in the picture, I'm not going to plug 4 in for my radius here. I come up with my formula, leave it all in terms of variables, and I don't plug in any numbers that might change over time. Like the radius is not always 4. Right? You have the sphere. This is going to look terrible. You have the sphere, and it's growing. It's getting bigger. The radius is increasing. So it's not always 4. What we need to do now is the next one. The next D is differentiate. We're going to find the derivative of our equation, but we're going to do it with respect to time. With respect to time. What this means is when you differentiate, you're basically figuring out at any one moment in time how fast is something changing. So we're going to differentiate with respect to time. So what that looks like is this. This is where implicit differentiation comes into play. So when I differentiate this whole thing with respect to time, well, the derivative of v with respect to time is just dv dt. That's how we write it. We're finding the derivative. Equals, and now on the right side, we're going to find the derivative of this with respect to time. So this is just our normal power rule. Like 4/3 pi is just a number. So 3 is going to come out and multiply by 4/3 pi. So that's going to become 4 pi. And then r squared. So that 3 came out in front and multiplied by 4/3, and then we reduced the power by 1. But remember, with implicit differentiation, when you differentiate with respect to x, you differentiate it and then you put dy dx. Well, here we just differentiated r with respect to time. So we put dr dt behind it. So this is kind of the most important part of related rates is after you differentiate, you put d whatever dt. From here, now it's kind of the fun part. The last S is substitute and solve. Like plug in the stuff you know and solve for the thing you're trying to find. Like this is the plug and chug part. So we're trying to find dv dt. That's what we're looking for. At this point, now that we have frozen time, that's kind of what we just did. We have paused time. Now we could plug 4 in for r. And we also know dr dt is 2. So we could put 2 in for dr dt. So dv dt equals 4 pi. And then 4 squared is 16. And dr dt we know is 2. And we could multiply all that stuff together if we would like to. And that would be 3264 pi. Is that right? 128. What am I doing? 128 pi. And then we have to put units. So it's kind of like we're finding velocity essentially. So it's going to be like units per second or whatever. In this case, volume is cubic centimeters. Volume is cubic centimeters per, in this case, we're minutes, per minute. That's how fast the volume is changing at the moment the radius is 4 centimeters. There's a lot going on, but I promise you, if you follow this DREADS acronym throughout, then you're going to be in good shape to get a good amount of points. That's the goal. Let's look at 3. If you want to try 2, feel free. I could put the answer up if you want to give 2 a shot. If you're not too confident, you can pause it, try it. I'll put the answer up really quick, and you can see. It's a resistor. There is no picture. There's no drawing. I list my rates. They give me the equation. I differentiate with respect to time. And then I plug in my stuff. So if you tried it, there you go. I lied. Let's jump down to 4 because 3 is the same. So let's jump to 4. Okay. A ladder is slipping down along a vertical wall. The ladder is 10 feet long, and the top of it is slipping at the constant rate of 10 feet per second. How fast is the bottom of the ladder moving along the ground when the bottom is 6 feet from the wall? That is a lot, and that's why I use DREADS. I'm going to use DREADS. I'm going to draw a picture. So we basically have this ladder leaning against a wall. So your picture doesn't have to be too great, but here's a ladder. There's my ladder climbing up. And what's happening is, imagine my pen's the ladder. The top is slipping down, which means the bottom is sliding out. That's what's happening. Okay? So imagine this ladder slipping down the wall, and the bottom is going out this way, to the right. I'm going to label this picture a little bit. It tells me the ladder's 10 feet long. Well, back in the problem up here, I said you can't plug any numbers in if they are numbers that will change over time. Well, if the ladder is 10 feet long, then the ladder is always going to be 10 feet long. So for this problem, 10 is actually a number I can put in for the ladder. It will never change. I don't know these numbers here, though. Like these numbers, like how high the top of the ladder is, will change over time because the top of the ladder is going down. And this X value will change because the bottom of the ladder is sliding out. So those are numbers that can change. I'm not going to label those. That's my drawing. And so you can see we have a triangle here. So we'll talk about that here in a second. Okay, and now I'm going to list my rates. So it says the top is slipping down at a constant rate of 10 feet per second. Basically, this y distance is getting smaller. I know the rate of change of y. They tell me that, dy dt. But since it's getting smaller, since it's decreasing, then that means the rate is negative. So it's going to be negative 10. And this is something you need to be on the lookout for because they're not going to tell you, hey guys, on this one, the rate's negative. But since we know that this is getting smaller, we know that rate is going to be negative. Okay, we're looking for how fast the bottom of the ladder is coming out when the bottom is 6 feet from the wall. So we're looking for dx dt. We're looking for the rate of change of this when x is 6, meaning when the bottom of this ladder is 6 feet from the wall. So that's the R in DREADS, the rate I know and the one I'm trying to find and when I'm trying to find it. Now I need the E. I need equation. I need an equation that links a triangle and x and y together. I need an equation that links a triangle and x and y. And so this is where your knowledge of, SOHCAHTOA, Pythagorean theorem. I mean, you guys are going to have, when you're dealing with triangles, you're going to have different things to think of. But since this is a right triangle, I know that x squared plus y squared equals 10 squared. Like I know that on this problem. Here's an equation that links x and y in this triangle picture together. So sometimes it's going to take a little thought to get that equation. It won't always just jump out right at you. So that's E. I am not going to plug any numbers in too soon. Do not plug numbers in until you differentiate. That is the biggest mistake students make. They'll plug in 6 for x right here. No. You can only plug numbers in if they are numbers that will never change, like 10 right here. The ladder will always be 10 feet long. So now I'm going to differentiate this with respect to time. So I'm just going to differentiate each term. The derivative of x squared is 2x, but then I put dx dt. That's where my implicit comes from. And then it's going to be plus 2y, and then dy dt. The derivative of 10 squared is just 0. It's a constant, so be careful there. It just becomes a 0. So that's the differentiate part. The last one is substitute and solve. Now I get to plug my stuff in. So I know dy dt is negative 10. I know x is 6. I'm looking for dx dt. If this is the thing I'm trying to find right here, that means I have to know all the other stuff. I have to know x, I have to know y, I have to know dy dt. So I know x is 6, so that's going to be 2 times 6 is 12. I know dy dt is negative 10. I need to figure out what y is, though. I don't know what y is. But think about this. We have now frozen time. When you differentiate with respect to time, you have frozen time. Think about how cool of a superpower that is. The ability to stop time. You just did it. Well, that means now, in this moment in time, if x is 6 and the hypotenuse is 10, I can figure out the y value right now at this moment. I can actually do the Pythagorean theorem to figure out what y is at this moment in time. I can do 6 squared plus y squared equals 10 squared. So sometimes you'll use these formulas to find out something else you need. So this would be 100 minus 36, square root that. Y is 8. So 2 times 8 times negative 10. And so that's going to be, let's see, 16 times negative 10, negative 160. So add 160 and divide by 12. So dx dt is 13.333. And then units, it's going to be feet per second, because we're finding a rate here. Dreads! We dreadsed it. All right. The last one we're going to do, because then you'll have some practice on your own, and you'll be able to ask me questions next time as well. So the very last one says we have a cone. All right, we have a cone. Looks like this. Has a diameter of 42 inches. This cone will always have a diameter of 42 inches and a height of 15 inches. Water is flowing out of it. It's like drip, drip, drip. It's coming out. It's dripping out of this cone, like a funnel, at a rate of 35 pi cubic inches per second. How fast is the depth of the water dropping when the height is 5 inches? Again, there's a lot going on, and if you don't go through dread, these problems get very, very confusing. So basically, there's water in this funnel. It's flowing out, and so, like, let's say the water is here. When the height is 5 inches, that's when we want to freeze time. Let's say that the height of the water is right here. Well, I know that if I'm dealing with diameter, there are very few formulas with 3D figures that deal with diameter. Pretty much all about radius. So I'm going to mark the radius of this thing as 21 inches. I also know the height of this entire thing is 15. I'm allowed to fill those in because the dimensions of this cone will never change. Now, the water level dimensions will change over time, like the height of the water will change. So I'm just going to label where the water is as an R, and the height of that water as an H. Those are things that can change over time. So here's my picture. That's the drawing right there. Now I'm going to go through my rates. I know the rate of change of, it tells us the water's flowing out at a rate of change of 35 pi cubic inches per second. That's rate of change of volume. So I know dV, dt. And since it's flowing out, that means that volume is getting smaller, so it's negative 35 pi, since the water level is decreasing. I'm looking for how fast the depth is dropping. So height, I'm looking for dH dt. And I'm looking for that the moment the height is 5 inches. So when h is 5. Okay. So now I'm looking for my equation. I'm dealing with a cone, and I'm dealing with volume. So we have to know the cone volume formula, which I would give you on a quiz or a test, and it's going to be 1/3 pi r squared h. I made a comment early on. You want an equation that links your two variables. I want an equation that links v and h together, which means I do not want this r in the formula. So here's how I make this happen. If you think back to geometry and similar figures, what happens here is we have similar triangles going on right here. We have this big triangle, and then we have this little triangle, and they are similar triangles. And what that means is that the side lengths are proportional. We can set up a proportion with our side lengths here. So if I would compare the radius and the height, that will always be in a ratio of 21 to 15. The reason I'm doing this, I'm trying to replace r to be in terms of h. That's my goal right now. I only want h in this formula. So I'm trying to figure out what is r in terms of h. That's what this is going to help me do. So if I multiply both sides by h and reduce, that's going to be 7/5 h. That means that this right here is what I can replace r with right here. I don't want r in the equation because I don't know dr dt. I don't know a lot about the radius, so I want it all in terms of height. That's what I'm trying to do. So some of you might be thinking, I don't know what you're talking about. Bottom line, whatever your variables are for your rates, you only want those two letters in your equation. That's what I'm trying to say. So I need to replace r with 7/5 h. The radius will always be 7/5 of the height. I'm still not going to differentiate yet. I want to clean this up as much as possible. Make your lives easier. If you try to differentiate this right now, you guys are going to have to do product rule because you have two different h's being multiplied. So don't do that to yourself. Clean all this up. So I'm going to distribute the 2. So that's going to be 49/25 h squared. And then multiply by this h, so that's going to be h cubed. So I distributed the 2, and that got me h squared times h is h cubed. And then I can even go one step further and multiply my fractions together. So 49/75. I don't know if that reduces. Does it reduce? I don't know. So now I'm going to differentiate this with respect to time. So dv dt equals, the 3 comes out in front, so I'm going to multiply this by 3 and reduce it. So that's going to be, if I reduce 3 and 75, that's going to be 1/25. So 49/25 pi h squared. But then I have to put dH dt. And then I substitute and solve. So I'm looking for dH dt. I know dV dt is negative 35 pi. And I can plug 5 in for h. So 5 squared is 25, which will cancel out this 25. So 49 pi. Divide both sides by pi, so those are gone. So negative 35 over 49. So dH dt is negative 35 over 49, which that does reduce. Negative 5/7 inches per second. They're not all going to be as crazy as this, but they could be. You know, just following that Dreads formula, understanding the concept, doing your homework and practicing and asking questions. I mean, that's how you're going to get better. There's only one way. You know, if you're struggling right now, you have to ask yourself, am I going to AL? Am I emailing and asking questions? And if the answers to those things are no, then you're not doing what you need to be doing. It's not going to get better. But I'm here to help you guys. So make sure you guys email me if you have any questions. And we'll practice this stuff next class as well. Peace.